So refractive index means for a light ray uh, goes from air to a medium, right? So then this is the normal ray, normal line. So then the angle between the incidence ray and the light is incidence angle. Angle between the refracted ray and the normal is the angle of refraction. Is the medium. So then refractive index means sine I divided by sine R. So here keep in mind I is always the angle in air when you are doing the questions, right? So R is always the angle in the medium, and the refractive index is a property of a medium. We have discussed that, and also for a denser medium, the refractive index is more. The value is higher. So that's what we discussed last time. Okay, right. So now consider a situation like this: a light ray goes from uh, denser medium into the air, right? So then whatever the medium into the air, right? So then this is the less dense medium. So the light ray comes like this, and this is the normal ray. Yeah, can't you see? Oh, okay, now okay, right? Right, so it turns away from the normal, right? Now what will happen if I move this towards that side? Move the incidence ray in the medium. So that means this angle in the medium, if I increase it, what will happen to the light ray? So that means a second ray is coming like this. What will happen to the refracted ray? It will come further down. This one will be coming down, right? So then again, so if a light ray is coming like this, so then it will be refracted. So then if I change the angle of incidence, so then this ray is coming down a little bit. So that means if I turn this ray inside the dense medium, so then the less dense medium, the light ray will come down and down. Okay, so when you keep on increasing like that, at some point, right? So when the light ray is increasing like this, at some point it should go between these two interfaces, isn't it? Is it understood or no? Right? So if I keep on increasing the incidence angle inside the denser medium, right? So then the refracted ray in the air is also coming down and down. So then at some point the light ray will be going between the interface of the mediums, right? So that means if we draw only that situation, so then this is the normal ray, this is the interface, and if you draw the light ray, so then at some point it will go in a path like this. So then this triangle will be 90 degrees inside the air, right? So then when this happens, the angle inside the denser medium, we call it as the critical angle. Critical angle. Is it clear? Right. So then let's say this is the critical angle. I'm doing the same thing again. This is the critical angle. So then if a light ray comes with a small angle than the critical angle like this, so then the light ray will be refracted like that. So then this angle here, it is less than the critical angle. So then what will happen if a light ray comes with a much larger angle than the critical angle? Now this angle is greater than critical. So what will happen? Any guesses? Sorry? Right. Now here what is happening, right? So in this case, right, uh, so here what is happening, if we increase this one, this light ray is coming down. So then when this happens, so then the light ray has gone through the between medium. So then if we keep on increasing this one, what will happen? What could happen? it should be reflected back like this. Okay, so it will be reflected back to the original medium. So then this situation we call it as total internal reflection. So that means all the light will be reflected back to the same medium. Okay, again keep in mind the critical angle means, right, so when the light ray is going from denser medium into less dense medium, dense to less dense, right. So if the refracting refraction angle of refraction, if angle of refraction is equal to 90, so then angle of incidence we can call it as the critical angle. Okay, so then if the incidence angle is less than the critical angle, no problem, the light will be refracted into the air or whatever the less denser medium. But if the angle is more than the critical angle, what will happen? So then no refraction. The refraction means it has to go into the other medium, it is not happening. The light will be reflected back to the same medium, right. This is what we call as total internal reflection. The uses of this total reflection, internal reflection, we'll discuss it later, right. For now we'll just focus on the critical angle. So then you have the notes. uh, Remind me to discuss about this practical, right. Critical angle means consider light ray enters from denser medium into less denser medium. If the angle of incidence is less than r, if the angle is incidence increase from 0, the light ray will refraction will increase always as well. When the angle of refraction is 90 degrees, the angle of incidence is called the critical angle, right. So in this space, draw these two figures. First one with a small angle like this. You can say the critical angle is this way, right? So when the angle of refraction is 90, the angle of incidence is called the critical angle, or you can say, right? So now this is a condition, right? So whenever you say the critical angle, if they ask what is meant by the critical angle, this is important. They have to say it is going, light ray goes from dense medium into less dense medium, right? So then if the angle of refraction is 90 degrees, so then we can say it is the critical angle. Or else what we can say is, if the refracted ray goes through the interface, angle of incidence is equal to critical angle. You can say either way. Now let's say we, how can we connect this one into the refractive index, right? Now this is the medium, this is air. So then if we write the equation for the refractive index, so then it is sine I by sine r, right? So then sine I, remember I told you I is the angle in the air whenever you are doing these calculations, for these calculations only. So then angle in the air is 90 degrees, angle in the medium is c. What is the value of sine 90? I have a calculator. What is the value of sine 90? Oh, okay. Right, so then sine 90, if you type it in the calculator, you will get that value as 1. So then we get n equals 1 by sine c, or else we can use this as sine c is equal to 1 by 1. So then this relationship we use to calculate the critical angle for any medium. Understood? Right, if you know the refractive index, you can calculate the critical angle for a given material. Right? Now, yeah, this is also, I think, mentioned in your note. Uh, at here, mm, right, so first mention about this total internal reflection thing. Space. And remember, so then this is the total internal reflection I discussed, right? So it is a reflection. So the normal reflection law is applied. So that means the two angles has to be equal. Okay, right? So draw that figure there. After that, we will do the calculation about that critical angle. By this question. Right. So let me know once you're trying. Right. So first try, then we'll discuss. We have to mention the light goes from denser medium to less denser medium. Okay. But you mention it as incident angle, no? Then fine, right? So when you mention it as incident angle, so that means it's going from denser to less denser. Okay. Uh, right. So yeah, we'll discuss anyway, right? So then we know we can use the previous equation. Sine c equals 1 over n. So in sine c equals 1 by n. For water we can use then sine C equals 1 divided by refractive index is 1.33. So then C for water is sine inverse 1 by 1.33. What will we get? We should get something closer to 48. 48.7. 48.8 or 48.7. Right? So if you use the same method for glass, sine C is equal to 1 by 1.51. Yeah. So then C is equal to, that means for glass, sine inverse 1 by 1.51. So then this should be equal to 41.8. Okay. Okay. That's it about the this one, right? So then we'll do another question. What is the critical angle for this glass? Again, the calculator problem. You can use your phone. Yeah, how much? Yeah. So then sine C is 1.6. C is sine inverse 1 by 1.6. This is 38.6. Right? Or else we can just round it off 37. That's fine if you want. Right? Okay. Calculate the angle X. Right, actually, before you calculate in the X, right, you should have the Y angle, right, isn't it? Right? Yeah. So then if you consider this as 30, right, so remember if we want to use refractive index, n is equal to sine I by sine R. So then refractive index is 1.6. Sine I is the angle in air. So then, but you have to use this angle. So then that is 60 degrees. So then sine 60 by sine R. So then sine R is sine 60 by 1.6. Right, what do you get for the R? Then how did you do it? No, actually you need the R, that means the Y, right? So sine 60 by sine Y, because you can't find directly the X, right? So I wanted to, I was going to give you the find Y first, but you had to find the R, otherwise you can't find. Okay, so then sine inverse, whatever this answer is, the R value, so it is coming as 32.7. R is 32.7. I will just round it off to 33. So this is coming as 33. So using this angle as 60. Is it okay? Right. So then x is equal to 90 minus y. Now this is y, not r, y. Okay. So then y is 33. So then x is equal to 90 minus 33. That means 57. Nah? Okay. So then this is 57. Right. Next one. Explain what happened to the light ray at point B. What will happen to the light ray when it reach point B then? Why not? Is it less? Now, y is less than critical angle, but when it comes to point B, angle of incidence is this angle, right? The one I'm shading. What is the value of that angle? Is it y? No, that is x, isn't it? Right, this is y. This angle is 90 degrees, so then this is 90 minus 33 means again 57. Or else you can think now this is, you have lines like this, so then these angles I think you have learned as alternate angles or something. So then either way this angle is 57, which is greater than the critical angle. Critical angle is 38.6. So then the light will be totally internal reflection. It will happen totally internal reflection. So you have to give it as a comment, right? So then at point B, so the angle of incidence is equal to 57, which is larger than the critical angle, right? So therefore, total internal reflection will occur, or the light will reflect back to the glass block. Either way, you can say. Okay, how did you find x then? Mm, that is not x, no. It has to be y, right? So in the refractive index, we are using the angles between the light ray and the normal ray only. Okay, right. Yeah. Then now, okay, we'll do some questions again later, right? So I want to go back to the part we skipped here. But, no, we'll come back to that one later, right? We'll finish this part. Right, so then weak reflection, right? So then what we discuss is this part is what we call as the total internal reflection. Now, relative to this total internal reflection, not exactly relative, right? So there is another thing called weak reflection, right? Now we know if you go to a, like if you take like a water surface, right? So we can see some reflections from the water surface, but those reflections are not so clear as like a mirror reflection or anything, right? Even if you take like a glass window or a glass something, right? So transparent glass, so the light supposed to pass through the glass, but sometimes if there is like a lamp or something, right, so we can see a very weak reflection of the light from those glasses, right? That is because every time the light refracts, a small part of light will always be reflected, right? Now if you consider this way, right, so the normally if the light enters a denser medium, it will turn towards the normal this way, but every time this happens, a small portion of light will be reflected back, right? Now even if it is goes from the other way, right, so even if a light ray goes from less dense medium into a denser medium, or denser medium into a less dense medium, so it's always small amount of light ray will be reflected, right? So here also light reflected is there, so then this is what we call as weak reflection, right? And you can see the weak reflection and the total internal reflection are two different things, because in weak reflection light reflected partially, but the total internal reflection, the light is completely reflected. So
I
now
have
we
here
go
a
to,
very strong laser and a glass prism. Turning off the light, we see the ray
right. So then this red line is the light. So it is totally internal reflect. It enters from here through, this is a glass prism, right? So then it will be reflected from this surface and again from the other surface and reflected back.
totally internally reflect at our two glass to air interfaces. I have here a very
Right.
strong laser and a
So
glass
check
prism.
on
Turning off the
YouTube,
light,
right?
we
You
see
can
the
find on that one. There are a lot of videos related to this thing. As you can see, the light is like bending, right? That is because this light will be totally reflected through this water flow, right? Same. So light is totally reflecting, so that is why it is following that kind of path, right? So if you go through this YouTube, right, so there are a lot of videos showing the reflection, total internal reflection, right? So you can refer to them. So this is another one. Again with the prisms.
Because the incident ray striking this surface has angle more than the critical angle. Here also we see the total internal reflection and the ray deviates by 90 degrees. Amazing view. Eighty degrees. Here we see light ray simply escaping out when it hits the vertex of. Let's have some fun with two prisms. Behaves.
And so that's the path of the light ray. As the refraction is happening, right? So then if you go through the YouTube, right, you will find a lot of videos related to this total internal reflection, right? So actually this total internal reflection is a useful thing, right? If you go back to the board, right? So where do we use this total internal reflection, right? So now we saw the glass prisms, right? Especially 40 90 degrees, right? So that's mean glass prisms are used, right? So equilateral glass prisms are used to rotate the light by 90 degrees this way, right? So here it is reflected by 90 degrees, here it's also reflected by 90 degrees, so it will follow that kind of path. Now this kind of glass prisms, so they are most of the time we are using in like optical instruments such as binoculars, right? Now if you take binoculars, right, even sometimes like microscope, periscopes, so we are using the glass prisms as shown in this case, right? So then change in the direction of the light ray, right? So then this kind of techniques are used to reduce the size, the length of the binoculars, right? Also sometimes we use periscopes, just like seen in this second side, right? So periscopes used in those submarines when they're in the underwater, right? So if they want to see what's above the water surface, they send a small device, so then the device may consider this kind of prisms. Right, you can use mirrors also, but the thing is, if sometimes mirrors, the quality of the image formed by the mirror can be changing, depends on the thickness of the mirror, and also depends on the paint applied on the other side of a mirror, right? So then prisms are better to reflect the light using this method, so then they will provide very quality images of whatever the things that we are observing, right? So then that is one use of the total internal reflection, right? So glass prisms used in optical instruments, right? And another main use of this glass prism, the total internal reflection is what we call as optical fibers, right? Have you heard about optical fibers? What does it do? If you have, where do we use optical fibers? Internet lines mainly, right? So they say fiber optical technology and everything, right? So then they are sending those internet signal using optical fibers, right? So not only the internet signal, sometimes they use like decorations, right? And even in the medical procedures we are using optical fibers, right? So optical fiber is something like this. Now it is a tube with two layers, right? So inside we have one type of transparent material, it is covered with another material, right? So then if you look at the cross section, it will looks like this. So then this is like the cover, right? So this is the cover material. So then this is the, we call it as the core. So then if you look from the side view, right, so it might look like this. So the cover is going like this, the core is here, right? So normally the cover has a much less dense, less refractive index, and the core has a very high refractive index. So that means the core is the denser material, right? So then cover is the less denser material. So then when the light enters from one medium to another, right? So that means if a light ray enters this core medium, what will happen is, right? So then the critical angle for this kind of situation is very small, so therefore all the light will be reflecting back. So then from this surface reflects, so then this surface again reflecting, so then they are again reflecting, so then the energy or whatever the wave is traveling using the total internal reflection like this. Now even if it is placed like curves, right, so then the light can travel like this. So that is why we saw in the videos, right? So I showed you, right? So the that water stream, so as the water is coming out, so then the entire water stream is lit because of the light ray traveling as using these total internal reflections like that. Is it clear? Yeah. So then this is used, right? So now instead of light waves, right? So if you use like infrared waves, microwaves, so they are used to communications, right? So communication signals means such as mainly such as internet signals can be used using can be sent using this fiber optical technology, right? So then another use of this optical fibers is, right, sometimes they are used in decorations, right? Let's say uh, so optical fibers, sometimes you may have seen something like this, right? So they are lit, so then when the light is sent from one side, so they will pass through these optical fibers, so then from the other end it will lit, that means the light will be coming out from the other end, so then we can see it. That means the light is traveling using the optical I mean the total internal reflection, right? Another use is, right, so then this one, right, so this is I think mentioned in your textbook as well, as I remember, right? So endoscope technology, right? So then when doctors want to observe the inside of a body, right? So then without cutting the entire thing, right? So they make a small cut and they will send a small camera like this, right? Okay. So then what happens is, right? So when, right, you are looking from it, right? So then the light is sent using one tube like this, right? So when it reach whatever the object inside that we are observing, so then light, reflected light is coming through another optical fiber like this, so then we can observe whatever the thing that we need to observe without making a very large cuts or cutting, without doing any larger operation. So then this is what we call as endoscope, or we can say it's in medical procedures we are using this technology. Is it clear? Right? So that is I have mentioned here as the uses of total internal reflection, optical fibers, and the endoscopes in the medical applications and the optical instruments. Right? I guess clear, right? Right. Okay. I think I shared the PDF with questions, right, in the group. Okay. Diagram one shows what happens when a light. Diagram one shows what happens when the light is incident on a piece of transparent material. Ray of light enters like that. On diagram 2, draw the reflected ray from point X. Now that is the weak reflection, right? So in the reflection happens, right? So the angle of incidence equal to angle of reflection. So then it should be going like this, where this angle is also equal to 64, right? Now even if you don't measure and draw, right? So at least to the eye level, right? So when you're looking from the fig, just by looking, right? So then it should looks like 64 even if you don't measure it like that. Right, go to the next one. State the formula linking refractive index. Okay, you can try this part, and it goes till the next page, right? So give it a try and let me know. And if you need anything, just ask again. Uh, So then formula is the same one, right? Now normally, don't get it wrong, right? So even though it says refractive index, angle of incidence and the angle of refraction, there is no direct relationship between the angle of incidence and the refraction. We need the sine value. So then n is equal to sine I by sine r is the relationship that we need to write, right? So don't write just I by r. Show that the refractive index of the transparent material is about 1.7. So then we have to use this figure. So then it is sine 64 divided by sine 32. What will you get exactly? Okay. So 1.69, can round it off to 1.7. Yeah. State the formula linking refractive index and the critical angle. That also we discussed earlier. So then sine c equals 1 by n, or n equals 1 by c. Either way you can say. So then the critical angle is, we know, sine inverse 1 by n. 1 by n means here it is 1.69, or even if you want you can use 1.7, no problem. What do you get? Okay. Right, so I'm getting 36 point something. Really? On the phone? No. And 3, right? Even if you write as 36, that's also fine, because normally most of the time we are writing the answers to two significant figures. So therefore, if you write 36, no harm at all. Next one. Explain the behavior of the light at point Y and Z. What is happening there? Y and Z. No, I said all the all the parts. Really? Okay, try this one also. Finish the question. Hmm. Mm-hmm. Is it what happening at point C? No. At both points, we can say it's total internal reflection, isn't it? If it refracted, it will come out like this, isn't it? Yeah. So at point Z and Y both, right? So then Y and Z both total internal reflection is happening, right? Now how many marks there? 3 marks. So then this is only, you will get 1 mark. Why is that? Why is this total internal reflection happens? Uh, so now total internal reflection is also we observe when the light is going from dense to less dense medium, right? Otherwise, if there is no critical angle inward, right? So then total internal reflection happen as the light trying or trying to go from dense to less dense medium, right? But the incidence angle is larger than the critical angle, right? So those are the 3 points, right? So you have to mention the total internal reflection, and since it's 3 marks, right, so you may have to mention this part as well, because the light is trying to go from dense to less dense medium. Angle of incidence is greater than the critical angle. Now, if it is like 2 marks question, this second point, second middle one may not be necessary. So only the angle comparison and the total internal reflection will be enough, right? So therefore, whenever you are doing a question, right, so remember, check how many marks allocated, especially for this kind of explanation questions, right? So then based on the marks, so you will be given, you need to mention some different amounts of points. Okay, right. Actually, that is the end of that light section, right? We need that small practical to be discussed, right? So we'll discuss it next time along with the sound lesson, right? So with that, I think we will be able to finish this lesson next week. No, not next week, because